Okay guys, we're going to talk about domain and range. So first, domain. So our domain for a function deals with the possible x values. Okay. Now since x stretches horizontally from left to right, anytime you are looking at a function's graph and you're trying to find the domain, you want to look for how it is stretched from the left to the right. Okay. Range deals with a function's set of possible y values. Okay, so let me go back up here for a moment. A function's domain is the input, and so that means the range is the possible output. So on a graph, if we're talking about the possible y values, we're looking at where does the function stretch from the bottom to the top. Okay, what are those possible y values that it's taking on? Okay, we're going to look at some examples here where we're trying to find the domain and range. And we have first the function y equals the absolute value of x minus 2. You can see it graphed for us over here. So our domain, our possible x values. Okay, so this is our input. So ask yourself, is there anything here that you can't put in for x and possibly take the absolute value of? The answer is no. You can take the absolute value of any number. Okay, you could always subtract 2 and then take the absolute value of any number. Graphically, if you look over here, you can see that this is stretching from the left to the right. It's a nice continuous curve. So that means our domain is all the reals. That's our symbol for all real numbers. Or you're going to see that we tend to prefer interval notation. So the interval stretching from negative infinity to positive infinity. Okay? Okay, so that's called interval notation. Now the range, this is the output or the possible y values. So remember, this is from the bottom to the top. Well, you can see here on the graph that it's bottoming out here at a height or a y value of 0. And then it goes up to infinity from there. So for our range, we're going to use interval notation. So the smallest y value that it could take on is 0. You can see it does not stretch into negative territory, so it's not going to take on any negative numbers. So our range is from 0 to infinity, and we want to include that 0. So we use a square bracket to indicate that we want to include that number 0. Okay, so that's using, again, what we call interval notation. Okay, so there is another way of expressing this range. If we want to use what we call set builder notation, we could say that our range, so this is another way of doing this, we can say that our range is all y values such that y is greater than or equal to 0. That's one way of expressing it. Or sometimes instead of that forward slash you see a colon and then y is greater than or equal to 0. So very similar. Okay, this last technique here, these two, this is called set builder notation. It doesn't matter which one you use. Our textbook and IB and myself, we tend to prefer interval notation. Okay, but at the end of the day, it really doesn't matter what you use to express your domain and range. Okay, in our next example here, we have y equals negative square root x minus 2 plus 1. We can see a graph for us. It appears to start here at the point 2 comma 1, and then it goes down and to the right from there. So our domain here, our possible x values, you can see that, well, 2 is our starting x value, and then it stretches to the right. So our domain is 2, including that 2, so we need a square bracket, to infinity. So this suggests that anything less than 2 is not possible. And think about why. Look at the equation here. If I were to plug in something like 1, or even 1.9999, this would give me a negative underneath the square root because we're subtracting 2. We know we can't square root a negative number, so that is undefined and therefore outside of our domain. Keep in mind, if we were to use set builder notation here, this would be all x such that x is greater than or equal to 2. But again, you'll see me from this point forward using interval notation for pretty much everything. So our range, all right, it looks like the highest y value it takes on is 1, and then it goes down from there. Well, with interval notation, we want to make sure that we're always going from least to greatest. Whether it's domain or range, it's always least to greatest. You can see with the previous one here, from 2 to infinity, that's least to greatest. So for my range, it's coming up from the bottom, which is really negative infinity, and reaching a maximum height of 1 and including that 1. So don't write it as 1 comma negative infinity. Again, go from least to greatest. Okay, so just jot down that quick reminder on that. Okay, so in our next example here, we don't know what the equation is for this function. We're just given a graph of it. And it's a segment, and we can see the endpoints on this segment. But notice at -3, 1, we have what we call a hole. Okay, it's an open circle, all right? So what that means is if we're first focused on our domain, so our possible x values, so the x values are going from -3 to 5, that hole means we're not actually taking on the value of -3. Okay, it's not part of the domain, but 5 is, since it's a closed circle. So in other words, on this function is -2.99999, but -3 is not on that function. Okay, so it ends at -3, not including that -3. So to say that we're not including -3, notice I used a rounded parenthesis. Okay, so we're going to use a rounded parenthesis anytime we don't want to include that number. The range, so now we're talking about from the bottom to the top. So this is going to be from 1 to 4, not including the 1, but including the 4. Okay? So the idea here is that this function, it could take on values bigger than 1, such as 1.0001, but it'll never actually take on 1 itself. Okay, take a moment and sketch this function here. This is another strange looking function where there's a couple pieces and we don't know the equation for it, but notice that we do have line segments where 3 of the 4 endpoints are closed circles. At 1, 4 we have an open circle. So our domain, our possible x values. So with the first piece here, it stretches from -4 to -1, including those values. Okay, and then it's going to kind of take some time off, and then it's going to stretch from 1 to 6, not including the 1 and including the 6. So to kind of connect these two together, we use this union symbol. Okay, it's the kind of looks like a lowercase u. You've probably seen it before. Okay, think of it as the union of two people when they get married, right? They come together. Our range, this is dealing with our possible y values. So as we look at this from the bottom to the top, the y values stretch from 2 to 5, and then they stretch from 3 to 4, but not including that 4. However, notice this piece on the right is within the inside of this piece here on the left. So our range is really just going to be from 2 to 5 because, again, this piece on the right is within this piece on the left. So it's kind of irrelevant. It doesn't matter that there's an open circle here at 1, 4. All right, that point at y value is hit over here, right about there. So the possible y values stretch from 2 to 5. Okay, let's take a look at this exponential function, 3 to the x. So our domain, well, if we look at the graph here, we can see that it's stretching from the left to the right forever. So this would be negative infinity to positive infinity. In other words, there's nothing you can't put in for x. You could always do 3 raised to any number. Okay, there's no limitations for x. Now, the range is limited. notice how our function does not stretch below the x-axis. That's because we have what we call a horizontal asymptote right here on the x-axis. Alright, so we have an HA, which stands for horizontal asymptote, at y equals 0. So a horizontal asymptote, this is a boundary line. It's a line that the curve is approaching, it's getting really close to it, but it's never going to hit it. Okay, so that suggests that our range here is going to be from 0, but not including that 0, to infinity. Okay, so if you were to try to plug in a number for x that is way over here in negative territory, something like, if we were to plug in y equals 3 to the negative 100, alright, what you would see is that this is 1 over 3 to the positive 100, and that is a number that is very, very close to 0. Okay, so our range here is affected by that horizontal asymptote. We tend to use dotted lines to represent our horizontal asymptote since it's not part of the actual function. Okay, with exponential functions such as 3 to the x, you're going to see these horizontal asymptotes embedded in the graphs. Okay, last example here, we have the function y equals 1 over x. So this function here actually has two asymptotes. We have a horizontal asymptote at y equals 0. Okay, there's a horizontal boundary line. We also have an asymptote over here which we call a vertical asymptote at x equals 0. It's x equals because it's a vertical line. So if we talk about our domain, this is dealing with our possible x values, of course. So as we move from left to right, notice how it takes on all x values except for 0. So we can express this as negative infinity to 0, but not including that 0. And then we're going to connect that with everything from 0 to infinity. Okay, so it takes on everything except for 0. Now our range ends up being the same exact thing because notice if you were to look at your equation here, or look at the graph rather, we're working our way from the bottom to the top, and as we go from the bottom to the top, it's hitting every y value except for 0. Now let's look at the equation for a moment and just make sense of this. So go back to your domain for a moment. Why can't x be 0? Well, if x were 0, then this would be undefined, right? We can't divide by 0. So that's why 0 is not part of our domain. Well, why can't we get 0 for our y value? Well, in order to get a y value of 0 in a fraction, the numerator would have to be 0, right? 0 divided by anything would give us 0. Well, our numerator is always 1, so it's impossible to get 0, all right, for our y.